At this point, we've already talked about electrolysis, and we've talked about how it happens. So one of its basic applications is electroplating. So electroplating is basically the depositing of a metal at the cathode. So we already established to say in terms of an electrolytic cell, of course we know that there's usage of DC current and from an external source. So electrons as well, they move from the anode to the cathode. Okay, so understand that the electrons that go to the cathode, basically they get to react with the, we'll call them what, the ones that are positively charged, the positive ions, so that they basically get to be neutralized. So I'm giving an example of sodium, right? It will gain back an electron because the positive sign indicates that it had lost. Okay, so now what we are saying is what this solid that is being formed will be deposited on the cathode. So that process is what we call electroplating. Now what we want to understand basically is how we get to determine how much of it has been deposited. Of course, applying the Faraday's laws, where we know that time has got an effect, the voltage has got an effect, so all those things are to be applied here. So we use this information given to predict or determine how much of the mass will be deposited on the cathode. So in this case, we are looking at copper. So copper 2 plus is reduced. So copper is reduced by gaining 2 electrons, obviously, so that it gives us copper solid, right? Okay. So 2 electrons are the ones basically that are what gained in this case, since it's copper 2. And then if a current of 1.25 ampere is passed for 72 hours, what mass of copper is deposited at the electrode? Assume 100% current efficiency. The atomic weight of copper has been given. So a few basic steps. Each time you're looking at such a question, think of it in terms of charge, right? So think of it in terms of charge, which is denoted by Q, right? So we'll try to determine our charge. So Q is basically IT. Okay, so charge is basically the flow of current in a wire. So you are looking at it, the rate of flow. So you're looking at it in terms of a current, and then you've got the time. Okay, so charge is a product of current and time. So with that understanding, in this case our current has been given to be 1.25 ampere, and then we have time. Okay, so the time we've been told 72 hours. So now what you need to understand is the fact that ampere is the same as coulomb per what? Per second. That's why we say current is actually the rate of flow of what? Of charge. Okay. So coulomb per second. So we need our time to be in seconds. Now we've been given 72 hours. Now we understand that in an hour you have how many minutes? You have 60 minutes. Now in every minute you have what? You have 60 seconds. So if we are to determine how many seconds are in an hour, we would have to say 60 times 60, right? So we have 3600 seconds in an hour. Okay, so if that's the case, how do you convert the 72 hours? So we need our seconds to be on top, right? Okay, we need our seconds to be on top. So say 3600 seconds per every hour, and then multiply by 72 hours. Okay, so at this point we expect that the seconds here will cancel, the hour will cancel. So we're able to find now the only unit that is remaining there is the coulomb, if that's the correct pronunciation. So we have 1.25 multiplying 3600 multiplying 72. So what we have at this point is 324,000 coulomb. Okay, so we've determined the charge by using the current and have you raised that current and the time. So in terms of now determining the mass that is going to be deposited, we need now to use the Faraday's constant. So the Faraday's constant, the value is 96,485. That's the value of the Faraday's constant. Now what else do we basically get to work with? So we've been given the molar mass itself. Okay, so it's very important that we basically get to understand the units of Faraday's constant. So the units are coulomb per mole. So why am I focusing on the units? I'm focusing on the units because these are going to help us. Okay, so with that understanding, since we want to find the mass, we're interested in that our final unit remaining should be grams. Now the coulomb. So with the charge that we've calculated, I need also to mention that if you look at the Faraday's constant, the units are per mole of actually electrons. I needed to mention that. So in terms of multiplying with this part, we need to work with dimensional analysis by looking at the units. That's the best way of handling it. Okay, so obviously we expect that when it comes to the coulomb, it's on top for the Faraday's constant, so it has to go down. So the more of electron will go on top, so more like we are dividing, right? So more of electron on top, and then we have the Faraday's constant on the bottom. So that is coulombs. So we can cancel those units already. The coulombs have gone away. Now we need to cancel out the more of electron. How do we handle that? So we need to multiply by something that will help us do away with the more of electron. But let's not forget that our goal is to find the mass. So let me first go upon something that will give us the mass. So we're dealing with copper. So its smaller mass will give us a mass on top. So 63.546 grams per mole. Now that mole, I need to indicate that it's a mole of copper. Okay, per every mole of copper, there's 63.546 grams. Okay, what else do we need? Now we need to pay attention again to the actual equation. So you can observe actually that there are two electrons, these two electrons, okay, two electrons that are being produced, that are being gained per every mole of one copper formed. Okay, so now check that the mole of electron is on top there, so we have to have it down. So we have 2 moles of electron per every mole of copper solid formed. So you realize that this is now making sense because we expect that the mole of electron will cancel with that mole of electron, the mole of copper will cancel with this mole of copper. So the only unit that is remaining is what? The grams there for the mass. So if I grab my calculator there, beginning with a charge 324,000, okay, 324,000 divided by, let me multiply first of all by 63.546, and then we'll divide by what's on the bottom. On the bottom we've got the Faraday's constant, 96,485, and then a 2 as well. So the value that I'm getting here is 106.7 grams. So that's the expected mass of of what? Of copper to be produced. Okay? So with that understanding, we can now move on to the other part. We now have the complex question, which will break down. So if you are tired, I would recommend you pause the video and resume after, because this question is very important. Most of the concepts under electrolysis are going to be summarized as we answer this question. Okay, so if you have built confidence from the previous question, feel free to pause the video and try out all the questions. Of course, E is more related to the previous question. Okay, now let's start with the A. First of all, we've been told in an electrolytic device, of course, an external direct current, we understand that, is connected. Now, in this case, we are told we are using two platinum electrodes immersed in a solution, okay, of 1 molar concentration, copper sulfate, that is, at 25 degrees Celsius, which means that standard conditions. As the cell runs, copper metal is deposited onto one electrode. So that electrode, of course, we call it the cathode, and oxygen is produced at the other electrode. The two reduction reactions that occur in the cell are shown below. So these are the half reactions. Now, if you try to observe them, they are all written in the form of what? Reduction. Okay. So on the diagram above, indicate which electrode is the cathode, which is the anode, and the direction of the electron flow between the electrodes. So what do you think? So if you look at the diagram, they've given us a hint. They've told us to say this is a reaction that is happening on this electrode. Now, what kind of a reaction is this? So gaining of electrons, what do we call that? So we call that reduction. So that reduction occurs where? So this is the cathode. So that's actually where the copper solid is being deposited, even according to the equation itself. So electrons are coming from the other side, okay, which is the anode. So this is the anode. So we expect that it's at the anode where we have oxygen being produced. Okay. So we've answered the first question. Of course, just a reminder, the anode is always connected on the positive part of the battery. The negative, that's the cathode. So write a balanced net ionic equation for the overall electrolysis reaction that occurs in the cell. Okay, so we need to write the balanced net ionic equation. So one step that you can basically take to even answer that question is you need to reverse the oxidation reaction. So according to the question, we've already been given the reduction reaction, and because we've been told copper, of course, is being deposited, so it remains as it is. Now the other one is supposed to be reversed since it is the oxidation reaction. Okay, so we need to have one reaction gaining electrons, the other one losing electrons. So since we've been told on the diagram, we can see that electrons were being gained. So where were they coming from? They were coming from the other half electrode, or the other electrode of the anode. So we'd have to reverse it because that's where oxidation occurs, and oxidation is loss. Loss is indicated by the presence of electrons on the product side. So that means if we reverse it, we have water on the left in liquid state giving us oxygen gas. What else? We have 4 hydrogen ions. We have 4 electrons. Okay. And then the other equation we have is copper 2 plus. So that one is as it is. So we have copper 2 plus 2 electrons giving us copper solid. Now you need to make sure that before you get to combine the two, the number of electrons being lost and gained should be balanced. So that means we have to multiply the second equation by 2. So it becomes 4 electrons, 2. And then we combine the left and the right hand sides. So for the left, we'll end up having water on top being combined. So water is of course in liquid state. being combined with 2 copper, 2 plus, in aqueous state as an ion. And then on the product side, we've got 4 hydrogen ions. We have oxygen gas. Okay. And then we also have copper in solid state. So that is the balance equation for this reaction. Okay. Now from there you should be able to determine, of course, the cell potential of this cell, okay, and the free energy for the reaction. So what do we expect? How do we calculate the standard cell potential? So I already told you the standard cell potential. If you don't want to confuse yourself, always just add the values. For the oxidation reaction, after I reverse a reaction, in this case we've reversed this reaction because it's oxidation, so the value of the reduction in potential changes, it becomes negative. So add negative 1.23 volts plus the reduction potential of the reduction reaction. What answer do you expect to get there? So negative 1.23 plus 0.34 volts, the value is negative 0.89 volts. So a negative value shouldn't be a surprise because this is an electrolytic cell. Okay, so an electrolytic cell, we have negative value of the cell potential. And then we also need to determine the free energy for the reaction. So the Gibbs free energy, I said it's negative n Faraday's constant and then the standard cell potential. So the number of electrons that were being transferred in this case were 4, which is denoted by n. Faraday's constant, which is 96.485, would just take it just to be the approximate value that is usually used as a constant, coulomb per mole. Those are the units. And then we need to multiply by the voltage, which is the cell potential there, which is negative 0.89 volts. Now I want you to know that volts is the same as what? Joule per coulomb, so that you can see the dimensional analysis there. So joule per coulomb there. So a coulomb will be able to cancel out. Okay. And then we remain with joule per mole. So after you multiply these values, you get a positive value, 340,000 joules per mole. Now you can divide by 1,000 to make it kilojoules, which will just be like 340 kilojoules per mole. Let me even put an emphasis by showing a positive value. So a positive value, of course, the positive Gibbs free energy and the negative cell potential show that this is a non-spontaneous reaction because there is usage of DC to force a movement of electrons from the anode, which is from the positive terminal in a battery, in an electrolytic cell. What is the minimum voltage that must be applied across the electrodes to drive the reaction? What is the minimum voltage that must be supplied? So the minimum voltage, of course, is just basically going to be the same value that basically was determined for the voltage. So we need a minimum of about, so we calculated 0.89, right? So minimum of 0.89 volts is required to drive the reaction. Anything less than that won't work. Okay, so now let's create some space to be able to answer the other question, which is the last part. So just allow me to remove the questions that we've already answered. Okay. So if you're tired, again, I'll repeat, feel free to pause the video and get to continue. Okay, so this is like related to the question that we've previously answered from the previous part. So we are told again an electric current of 1.50 amps passes through the cell for 40 minutes. So here we've got 40 minutes. Okay. So I told you to say the first thing that you'd want to do when you're trying to determine the mass, in this case, of course, asking us the same question, we need to determine the mass of that copper that was deposited on the cathode. So what do we do? So let's determine the charge. I said is current multiplied by time. Amps is the same as 1. That's coulomb per second. Remember, current is a rate of flow of charge. And then time, we also need to ensure it's in seconds so that we can just get coulomb as a result. So 40 minutes. So in a minute, you've got 60 seconds. So how about in 40 minutes? How many seconds are you going to have? So you have a product between 60 and what? So you have 40 minutes. In a minute, you have 60 seconds. Okay. So the minutes will go. And then you remain with the seconds. Now the seconds will also divide. Okay. So we'll multiply 1.5 by 40 by 60, giving us 3,600 coulomb there. So we've determined our charge, which is the first step. Now don't forget that we apply the concept of Faraday's constant. Faraday's constant is 96,500. This is the rounded off value. Okay. So I told you the units here are what? Coulomb per mole for Faraday's constant. Okay. Now we also need to take note of the cell, the half cell reaction itself. So according to the half reaction there, we've got 2 electrons of copper. We've got 2 electrons being gained by copper. Yeah, I meant to say that. Okay. So what should we expect then? So let's try to use dimensional analysis to help us come up with an answer. So we have 3,600 coulomb as our charge. I'll get the Faraday's constant. So obviously, since I want to show the cancellation of the coulomb there, since I'm saying it's 96,500 coulomb per mole, I can write it in form of the opposite so that the mole can be on top. So say 1 mole of electron over 96,500 what? Coulomb. Okay. So far we can see the cancellation of the coulombs there. What more do we need? We also need the molar mass of the copper in this case. Okay. So the molar mass of copper is grams per mole. The units for molar mass is grams per mole. So it's 63.55 grams per mole, of copper. Now according to this reaction, we are told 2 electrons are what? 2 electrons are basically gained by every mole of copper. So per every mole, so we need to make sure we write it in the way that it will cancel out. So per every mole of copper, we have what? We have 2 moles of electrons being what? Being gained. Okay, let's try to see now where the units have ended at this point. So mole of copper can cancel there. Mole of electron can cancel there as well. So in summary, the things that have been used in the calculation, we are using the charge. Okay, we're using the charge, Faraday's constant, molar mass, and also the electrons. Okay, so dimensional analysis will be able to guide you to come up with a basic calculation of determining the mass. So if we multiply what is on top, 3600 by 65.55 divided by 96,500, which is on the bottom, and also 2, we'll be able to get a value of 1.19 grams of copper. Okay, so that's how simple electroplating calculations are. Now, just to apply a bit of stoichiometry to answer the last question. Okay, so let's take note of a mass that has been determined. 1.19 grams of copper. So the question says calculate the dry volume in liters measured at 25 degrees Celsius, and the pressure has been given there. So first of all, the formula, without even wasting your time, we use the ideal gas equation because we're dealing with a gas there. Okay, so PV is equal to nRT. So if we are to find the volume will be equal to, you divide by pressure on both sides. So you have nRT of pressure, right? So take note, pressure has been given, the temperature has been given, gas constant is also always known. Okay, so 0.0821, and then we're just remaining now with N, which will be now the number of moles of the oxygen gas that we expect to be produced there. So take note that we'll just use the balance equation to help us, the balance equation that we basically came up with. So the balance equation that we came up with, which was representing the entire reaction, we had 2 water molecules reacting with 2 copper molecules. But of course I need to focus more on the product side, because that's where we have the ratio between the copper being produced. So we had copper solid plus what? Oxygen gas. So these are in the ratio of 2 to 1. So per every 2 moles of copper being produced, there is a single mole of oxygen being produced. Take note of that. That's according to the balanced equation for the entire reaction. Now, we've also determined the mass of copper to be 1.119 grams. Okay, so how do we find the mole of any given substance? So number of moles is equal to mass over molar mass. So this mass divided by the molar mass. So divide by the molar mass, which in other terms is multiplying by the reciprocal of copper. Okay, so remember the units for molar mass is grams per mole. So 1 mole per every 63.55 grams of copper. So that is just to show the cancellation of what? The units, or we are just dividing, in other terms, we are dividing the mass by the molar mass to get the number of moles. So this first calculation will give us what? The number of moles of copper. Okay. Now the number of moles of copper we are now going to use this ratio between the number of moles according to the equation that are being produced. Okay, remember this is a ratio according to the equation, the balance equation. So after determining the number of moles of copper, we're able to use that ratio to help us determine the number of moles of what? Oxygen. So if we want to find the number of moles of oxygen, then we need to make sure that the oxygen is on top. So multiply by the oxygen will go on top. Every mole of oxygen, there are 2 moles of copper solid that are produced. Okay, so at this point where the equation has reached, you are sure that we've now determined also the number of moles of what? Of oxygen that had reacted in that reaction. So after performing your calculations on your calculator, you should be able to get 0.00936 moles of what? Moles of oxygen. Okay, so if we want to find the moles of oxygen, we need to multiply by the molar mass. So 1 mole per every 63.55 grams of copper. So 1 mole per every 2 moles of copper being produced, there is a single mole of oxygen that had reacted in that reaction. So after performing your calculations on your calculator, you should be able to get 0.00936 moles of what? Moles of oxygen. that had reacted or that was produced at the anode. Okay, we can now use our equation since every value is available. So our volume is equal to nRT, where n is denoting the number of moles, which we've calculated to be 0.00936 moles. The gas rate constant is 0.0821 liter atm per mole, and then per Kelvin. So the 25 degrees Celsius that we have in our formulas, we use Kelvin. So you add 273, you'll be able to get 298 kelvins. All these values are to be divided by the pressure, which has been given to be 1.16 atm. Okay, so what do we get there? So multiply what is on top and then divide by what's on the bottom. So the volume that we expect to be produced, considering an 100% efficient of the current that was used, we end up with 0.197 liters.